So, welcome to a new course. It is a new course to our YouTube channel. I will try to post videos on this course. The name of the course is Differentiation on Array. Okay, that is the name of this course. So derivative in R. Okay. So what is the definition of derivative in R? Let me write. What is the drawback if we impose the same definition in Rn? Okay. In first years, we learned derivative or differentiability in real number. Okay. So what is the formal definition? Formal definition is what in R? Formally, a function f R to R is said to be differentiable. It is called differentiable at a point at some point R. At some point A belongs to R. Differentiable at A belongs to R or C belongs to R if the limit I will write limit as LT. Okay. H tends to 0, f of C plus H minus FC by H exists. This is sometimes phrased as limit, x tends to C. Okay, it is sometimes said as limit x tends to C fx minus fc by x minus C. Whatever. So in anything, so this was the definition in R. Fine. But okay. But is so analogously, if we define definition in Rn, then does that definition holds? Let me examine it first. I will define the same thing in Rn. In Rn, n greater than equals to 1. Then we need to see whether it holds or not. But it does not hold. Okay. Why? The same age. Okay. I mean, this age, this is the same. Either I write this or this, take is at same thing. But in Rn, that definition if we define in Rn means, but in Rn means if f is a function from Rm to Rn, then the above definition then is invalid because you cannot divide two numbers in RM. Okay. I mean, see, if AP is Rm to Rn, then this is from Rn, this is from, sorry, this is from Rn, this is from also Rn, and this is somewhere, I mean, anywhere. H tends to 0, I mean, H is some element tending theta belongs to Rn, then, or Rm, anything, I will define it. Don't worry. I will define it. It will be a point of the domain set Rn. Okay. Wherever the domain set, this will be the point there. Because how you did then add C plus H? Okay, C is a point of Rm, so it should be a point of Rm here. Anyway. Anyway, if M and N are R, most possibly, I mean, M and N greater than 1, then these things from the domain codomain Rn, this is from Rn, and this is also from Rn. So how you divide two vectors there? The division is in more than one dimension is not defined. So you should convert this to R. You should convert these things into some entity of R. So one thing is do this taking norm. This norm is from Rn. This norm is from Rn. The norm is Rm. So then you will finally get something interesting in R. Then the division is valid. I mean, at least the division is valid, and you can think about the limit. Okay, let me write, and it is denoted by okay. Then you need to introduce concept of norm. I hope you all know the concept of norm here. Okay, it is a classical concept used in metric space, topology, linear algebra, functional analysis, everywhere. So observe that. So I will take that definition. Okay, I will use this thing. See, if R to R is differentiable at any point, then how I could generalize this? Is differentiable at C belongs to R, then we have what we have? Limit H tends to 0 if C plus H. This is the definition, and this is equals to F plus C. So do one thing. I can multiply H tends to 0, so H not equals to 0. So in the right hand side, I can multiply H by numerator and denominator, take this thing this side. So that will give me limit H tends to 0 f of c plus h minus fc minus hf dash by h equal to 0. Right? You agree with me? I think. That is limit. It is limit, okay? H tends to 0. Zero. Here we don't need to we don't need to worry about uh, we didn't need to worry about which zero is from which Rm or Rn because we are in both in R. So H will be 0 from R. Okay. So in other words, can say we can say that in other words, what we can say that there exists. So observe first that if I define f R to R by f h equal to f dash c into h, that is a linear transformation because this thing acts as a scalar. So you can think that as an alpha. So if h equal to alpha h, for alpha is some fixed scalar, that is a linear transformation. I mean, that is same as fx equal to alpha x. So these things is a linear transformation. So what we can now say, we can say that there exist, I mean, reformulating this, we want to reformulate into some different language. And what we will get, there exists a linear transformation lambda. Suppose we name the linear transformation as lambda. From here we are taking R to R, such that obviously lambda is, I mean, it is defined by minus fc. So this thing we defined as lambda h. That is the another definition of differentiation. So here that is another definition of differentiation in R. What? A function f is said to be differentiable if R to R if there exists a linear transformation lambda from R to R such that this condition holds. Now I will now generalize this concept. I will now try to generalize this. I will now try to generalize this concept in function from Rn to Rn. So let me write as definition. That f is a function from Rn. I have no restriction on n and m. They are not necessarily one. Okay, m and n might be any natural number. Then f is okay. Take a point. First, take a point that a belongs to Rn. So when f is differentiable in Rn, then f is said to be differentiable. At a if there is a linear transformation lambda. Let us define the linear transformation lambda from Rn to Rm is that the following condition holds. Such that h tends to 0. This ratio, what you write, I don't know. Yeah, now I need to introduce the concept of mod or norm, whatever you are saying. If a plus h minus if a plus lambda h, this by mod of h equal to 0. Okay. Observe that this belongs to Rm. So this modulus is taken Rm, and h is a point of Rm domain. So this norm or modulus, whatever you are saying, this belongs to Rn. So these two mod are different mod. Okay, but one similarity between them is this after doing modulus, this belongs to R, this belongs to R. Now I can compare this quotient, and this 0 is 0 of Rn. Obviously this 0, but this 0 is 0 of R. Why? Because now I am in R, because this is in R, this is in R after doing the modulus. So we are observing the behavior when h tends to infinity, 0. So if that ratio is equal to 0, then that is called as differentiable at 8. Remember that modulus in the numerator is plus m, and the denominator is modulus. H is a point of Rn, so it will be modulus in Rn. Okay. Sometimes the linear map or the linear transformation lambda which we earlier defined from Rn to Rm. This is sometimes same notation. This is sometimes often in some book denoted by d of Fk. D of Fk. D stands for differential. Okay. So it is differentiable at a point. Now, when it is differentiable, it is differentiable at every point. A function is differentiable at a okay. It is differentiability, definition of differentiability at A. But when so if f is differentiable at every A belongs to where Rn, then f is said to be a differentiable function. Because differentiability at one point does not ensure that it will be differentiable at some other point. Right? But question, or a question can come, is the choice of the linear transformation lambda is unique or not? So if it is unique, or I can get another linear transformation, suppose lambda dash, such that it also holds for lambda dash, the definition. Okay. Then it will be a problem, right? Because if any in the same differentiation, if we are getting two different linear transformation, then this will be a problematic case, because that might the differentiation is dependent upon the linear transformation. So being two different linear transformation might give two different result. So that is our next theorem, and the answer is yes, it is unique. That is our next theorem. That is our next theorem. So I assume that. So let wait f from if Rn to Rm is a differentiable function, or you need not be differentiable. Differentiable at a point is sufficient. That A belongs to Rn. Then there is a unique linear map of lambda such that what holds limit h tends to 0, the ratio f of a plus h minus a minus lambda h by okay. That means that is what I'm saying. Choice of lambda or DFA is unique. So I can replace, if I can prove this then in my definition, I can replace A by the word A by the word Z. Okay. So I need to prove this. Suppose there is another linear transformation that will satisfy this. Suppose we name is at lambda dash Rn to Rm that satisfies limit h tends to 0. The same ratio f of a plus h a lambda dash h, this thing by divided by h goes to 0. Suppose we assume that. Okay. Now we let assume we let g h, or we assume this reference or this increment. Let this increment function, so it is functional increment. It is a after time t I am going to a plus h. Okay, so this is incremental function or delta of f. We assume that g, this increment of f. So you can say this is then g of h. Now I will show that limit, I mean g of h minus f of h equal, sorry, lambda of h, that is, sorry. I will show that lambda h minus lambda dash h equal to 0 for all point. Okay. For this I need to this function. Then what is limit h tends to 0? Lambda h minus lambda dash h. Right. This I am again saying that I am writing the h and h as same. Okay. It is my bad, my mistake, but I am habituated to write in this way. So don't think they are different. That is equals to lambda, limit h tends to 0. So I can plus minus this gh, right? No problem. This is lambda h minus gh plus gh minus lambda dash h divided by h. This is the same thing. So now I can apply it is a non Rn is mode is a metric. Metric satisfies triangle inequality. So I can apply that triangle inequality and apply the limit separately. This is nothing but This is lambda h minus gh. I don't need such a big sign. Limit h tends to 0. Again, there will be lambda dash h minus gh by this. Fine. Fine. No problem here. Now observe that this thing this thing is 0. If you put the value of gh, this thing is 0. Also, this thing is also 0. This thing is 0 and this thing 0 we assumed here because lambda already satisfies the linear transformation. So we assumed lambda dash was another linear transformation satisfying this. So the both limits are 0. So but in I can say that, but this is not established yet because what I am getting here, then this thing less than 0 is not possible. So it is not less negative quantity because there is mod. Mod is always positive. Thus, limit h tends to 0, lambda h divided by h. This is 0. Okay. But we need to prove that. First of all, this statement is depends on this thing. Limit h tends to 0. And I mean, so I need to prove lambda h equal to lambda dash h. But there is a limiting condition. So my theorem is not established yet. So I will use this as a tool to prove the next step. Now I will prove for anything. Let sorry, this is not limit. Let x belongs to Rn. Then if h tends to 0, h tends to 0, then xh also tends to 0. So xh tends to 0. Now I will replace h by xh because that statement holds for every h tends to 0. So applying this in the previous equation, we get limit I mean what I have said. So that means that, so let's just 1 minute, one mistake is there. Then if tx tends to 0, if it happens, then obviously t tends to 0 because if, sorry, it is if then t is a parameter or variable. So we apply this thing on tx. Now I can replace h as a tx because it holds for all type of h. That means this is limit now tx tends to 0. Replace everywhere tx, lambda tx, lambda dash tx. I can do this. Okay. Now see, t is a scalar. X is anything. We treat x as any arbitrary vector. Now we do t is a scalar. This thing. And lambda is linear transformation. So it will be again tx, sorry. And lambda is a linear transformation. So t will come outside. Just okay. We assumed here t as a scalar. X is a tuple. We are multiplying t with each tuple of x. So it is tx. So t will come outside. T will come outside. That means that will be limit t tends to 0. And t will come outside means mod t and mod t will cancel out. That means lambda x minus lambda dash x into modulus of t. Here modulus of t, modulus of x. So it will cancel out. We will be left with this thing. Okay? We will be left with this thing. But observe that this term is independent of t. So I can remove this thing. That is, sorry. That is actually this thing. But what is this exactly equal to? This is 0 by this theorem. This is 0. That means this is 0. But x is non-zero. So norm of x, modulus x is also non-zero. So this 0 means this is 0. So modulus of a number is 0 in any Rn. That means these numbers are equal. That is the proof. But limit tx tends to 0, lambda of tx. So let me write it here. Tx tends to 0. Okay. But limit tx tends to 0. That means lambda of tx minus lambda dash of tx divided by tx equal to 0. But that is equal to this term. This term. But so lambda of x, this is 0. minus x non-zero. X is non-zero where? X is non-zero in Rn. Okay. Which implies lambda x equal to lambda of x. But x was then arbitrarily. So actually lambda equal to lambda dash. Okay. So the proof is done. So one question you might have that lambda agrees with lambda dash on Rn minus 0 because x was chosen in from Rn minus 0. But we remember that any linear transformation maps 0 to 0. So lambda will also agree to the point 0. So lambda agrees in whole Rn. They are actually equal. Okay. So as long as far as we mentioned, we have discussed so far. There, remember the the h or I mean which is defined as d of fa, d of dfa at a is a linear transformation from into. So I will so an example. It is a very easy example. What is the derivative of sin x? Let f r squared to r be defined as let x1 comma x2 equal to sine of x1. So I need to find out whether it is differentiable or not. We need to check about the differentiability of f. Okay, that means we need to find the linear transformation. That means we need to find the linear transformation r square to r such that linear transformation, if we linear transformation lambda such that limit h tends to 0, f of you can say a plus h minus f a, or here f is two dimensional, so I can write a comma b. If we represent a point by a comma b, two tuples are there, so a plus h comma b plus k minus f of a comma b plus lambda of lambda. So it is a linear transformation. So h comma k. H is now h comma k by h comma k equal to 0. So what is the linear transformation here? So what is the derivative of sine x1? It is cos x1. So the linear transformation is cos that thing into h1. I mean, okay, I am defining it here. Let us define the linear transformation lambda by lambda of x1, x2, which is sine x1, or x1 is there already, right? So it is x. Now it is a derivative, so first component will be there, so it will be a. Why I'm writing here a? Because observe that the definition, the linear transformation was what? F dash c into h. So here, what is this thing? Here this is sine, so it is cos of x1. But I am deducing it at, I mean, a comma b. So what is cos of x1 evaluated at a? It is cos of a. Sorry, this cos, it will be cos here. Then limit h tends to 0 is f. What is a plus h, b plus k? I am putting the value here now. Now f is sine on the first component, so it will be sine a plus h. And what is f a comma b? It is sine a. And what is this thing I have defined here? It is, so lambda x1, x2 is this. So what is lambda h comma k? It will be x1. So what will be lambda h comma k? It will be cos a h1, sorry, h, this mod of this thing, still mod of this thing. This is 0. But observe that, okay, now I am not even observing, I am making direct conclusion. This can be written as is equals to fraction of sorry. This can be written as this fraction sine of a plus h minus sine of a minus cos a h divided by h. Sorry, this is equal to 0, I need to solve. So what had happened? Because in the denominator, it is equals to, you can assume this is at h square plus k square, which is so in the denominator, I have reduced the thing, so the fraction will be increased. But observe that now I am a condition from R to R, where my fx equal to sine x. Okay, and it is appropriate condition of f dash x at a. So this thing is 0. this is 0. So this thing is also 0. Then this limit sine a plus h sine a plus ah by h is 0, and we are done. So what is my linear transformation here? The linear transformation was x1 x2 sine of x1. Sorry, it will be cos, I think. Oh. The linear transformation is in this thing. This is cos of x1. So how to guess the linear transformation? The linear transformation is derivative of this function. You silently take derivative of this function into the second. It was on, I mean, into x1. How I take that might be a question, because see, there is my plan was to do this. So there is h in there. So in R, I want to follow the definition. So in R, what is the definition? There is some h. So there h means the first component. So therefore I take x1. My target was this actually, to apply this, so that it smoothly goes this. Okay. They are the same h. So sometimes, so this is a linear transformation, right? It is a linear transformation, lambda or df. It is a linear transformation. So sometimes, not always, as lambda is a linear transformation, we have a matrix basis conversion, coordinate coordinate conversion, I mean, of the scalars. Scalars not, it is a vector of the elementary basis vector, matrix representation of lambda, which is called a called the called Jacobian matrix of called the Jacobian matrix. So what is the order of the matrix? If lambda is order of, okay, I'm writing in the graph. What is the, I mean, order of the matrix? So remember that if T is a linear transformation from Rn to Rm, the matrix of T is a matrix of order m cross n. I mean, Rn to Rm, it will be of reverse m cross n matrix. Okay, so lambda will be so. Okay, the last is the definition of differentiability of a function. I already told that it is if is a differentiable at every point, the domain of its domain, then it is called differentiable. So if a is A is subset of suppose Rm to Rn. If f is differentiable at every point of its domain, then it is called differentiable at a differential function. Okay, fine. So okay, an example of Jacobian matrix. In this case, what would be the example? So in the above example, Jacobian matrix and denoted by, let me finish it. F dash A at A plus 1. A is lambda is from Rn to Rm, right? Rn to Rm. If it is from Rn, then the domain will be from Rn. Okay. So in the above example, what is f dashed of A comma B? Because A is there AB. I mean f is in Rn, so I am breaking it in the tuple. What is the linear transform? What is the Jacobian matrix? The Jacobian matrix is simple. The Jacobian matrix is, what was the operator here? Cos A, right? So it will be cos A comma 0. I mean, it is a linear transformation. So if I input a vector, so observe that. Suppose if I input a vector and multiply this by cos A, and this is 0, and suppose there is h1, h2 or x1, x2, then I am getting by the for transport by that linear transformation, it is cos AX1. Okay, so this is the thing. So okay, I want to conclude the class here. Thank you.